big idea number 3, and this one is all about understanding chemical reactions. So, some of the main concepts. To talk through chemical equations, we first need correct formulas. Then we need to know how to write the balanced equation, and once we have that, we can use the coefficients in that equation to do stoichiometry calculations. We can also use that information to identify our limiting reactant, our excess reactant, our theoretical yield, percent yield, and so on. And then a couple of specific situations within chemical equations. We've got solutions as a specific type of reaction, and if we're talking about solutions, we need to understand concentration. We need to understand aqueous reactions, things like solubility, things like our acid-base reactions. Redox reactions were another type of chemical reaction. Now, most of the redox reaction information is being excluded from the AP test this year, so everything on electrochemistry. You are, however, still expected to be able to identify a redox reaction, so we'll talk about that later. On that note, although electrochemistry is not on the AP exam this year, if you're looking at this set of slides on Classroom, there are still some slides over electrochemistry in there. I skipped them in the presentation, but they're still in the slideshow. One, because I'm going to need them next year, so I didn't want to delete them. And two, because if you are bored or curious, you can still go through and see what else we would have covered, and count yourself as pretty lucky for not having to do the voltaic cell stuff. Finally, two small things that have come up in previous videos are the separation methods and some analytical techniques that we'll talk about at the end. So to get started, we need to start right at the beginning talking about chemical formulas. So as we know, the chemical formula describes the bonds and the ratios in a compound. So the letters tell us what elements are in a compound. The subscript tells us how many of each element is in that compound. And looking at a compound, we should be able to identify what type of bonding is used, as that'll affect the rest of its properties. So there's two types of chemical formulas. There's the empirical formulas, which have the subscripts as the lowest whole number ratio of each of those atoms, and then the molecular formula, in which the subscripts are the actual amount of each element in the compound. So for example, the compound C4H10 has the molecular formula C4H10. That tells us that in that molecule there are exactly 4 carbon atoms and 10 hydrogen atoms. The empirical formula for that would be C2H5, the lowest ratio between those two elements. And that would still tell us the relative amount of carbon to hydrogen, but it wouldn't tell us exactly how many copies appear in the molecular formula, in the whole molecule. However, if we had the empirical formula and the molar mass, we could figure out how many copies of the empirical formula are needed to have the correct mass, and so we could figure out the actual subscripts, the actual number of each atom in the molecule. A quick reminder, there were the special diatomic molecules that occur in nature. There's a little memory device down here to help you remember, but you get to have whatever notes next to you want for the exam this year, so you might just write these down as a quick reminder. Alright, a couple important reminders for writing balanced equation. You got to start with the correct formulas for the reactants and the products. So you need to be able to take the name of a compound and write the correct formula for it. You can go back to units 1 and 2 if you need practice on this step. Once you've got the correct formulas, they're charge balanced or they match the prefixes used in the name or whatever it is, once you've got the correct formulas written, you do not change the subscripts, right? The subscripts tell you what compound, what substance is there. You can't balance an equation by changing the subscripts because that would change the material. Instead, you balance with coefficients in front of every compound to make sure we have a balanced equation. There are 5 sort of categories or types of reactions that you should be familiar with. The first is the combination or synthesis reaction, in which 2 elements combine to make a compound. Decomposition is just the reverse, where one compound decomposes or breaks apart into its pieces. We've got single replacement, in which a single element replaces one other in a compound. So we started with a single element and a compound. A took the place of B. We ended with one compound and one single element. Double replacement is very similar, only there are now 2 compounds, each seeing a replacement. Instead of one single element and one compound, we've got 2 compounds each with one atom swapping places in each, and we end with 2 different compounds. Finally, combustion equations are combustion reactions where a hydrocarbon reacts with oxygen. Remember, you always need oxygen for combustion, and the products of this will always be carbon dioxide and water. Alright, once you've got a balanced chemical equation, there are a lot of calculations you can do with it. The first one that we talked about was converting between moles of one substance to moles of another. And so we already know how to convert between grams and moles. We can use the molar mass from the periodic table. And once we have moles, we can use our balanced chemical equation to convert from moles of one substance to moles of another. And so this gives us a pathway to convert between grams of a substance as well. Do remember, it's very important, you have to get to moles before you can use the coefficients in your chemical equation as a conversion factor. There's no direct route between grams. You have to go through the moles first. A couple other important terms to remember. You should be able to distinguish the limiting reactant in an equation or a reaction. It's the one that you're going to run out of first. It's the one that prevents your reaction from continuing because you don't have enough of it to go on. So in the picture on this slide, we've got this before graphic in which we've got 10 molecules of hydrogen and 7 of oxygen. And we allow this to react until we end up with 10 water vapor or water molecules, 10 H2O, and 2 oxygen left over. So there was excess oxygen because there's some left over. There's no hydrogen left over, so that was our limiting reactant. The only reason these oxygens couldn't also react to form water is that we have run out of hydrogen. It limited our reaction. And so as you can see, even though we had more hydrogen to begin with, we started with 10 copies of it instead of only 7 oxygen. It was still our limiting reactant because every water molecule needs 2 hydrogen. So there was only enough hydrogen to form 10 water molecules. There was enough oxygen to form 14, because each water molecule only needs 1 oxygen. So there are a total of 14 oxygen atoms in here. Each water vapor molecule needs 1, so there's some extra, there's plenty. There was only enough hydrogen to form 10, and so we were only able to form 10 instead of 14. All right. Another important thing to keep in mind when you do calculations like this with stoichiometry and a balanced chemical reaction, one thing that you can do is predict how much product your reaction should form. on the picture before, we predicted that we should form 10 water vapor molecules. But that is your theoretical yield. That is what should be possible in a perfect 100% complete efficient reaction with no loss. In the real world, you will actually produce less than that. You probably won't have a perfect reaction. And so in the real world, you have an actual yield, which is less than or equal to your theoretical yield. For all practical purposes, it's less than your theoretical yield. You really don't have a perfect reaction ever. It's theoretically attainable, but not practically for the most part. Now, if you know both your theoretical and your actual yield, you can calculate your percent yield, which would give you a measure of how efficient and how complete your reaction was. A couple quick notes on some chemical analysis techniques. One example that came up before, I believe in Unit 2, was a chemical analysis to determine a percent composition. So in this example here, we're trying to find a way to determine the percent of sodium sulfate that's present in this mineral denarite. And so what we're doing in these images is we start by crushing up the mineral and extracting all of the sodium sulfate out of it and into water. We know sodium sulfate is soluble, so it's all going to form solution with the water. And so we had a certain mass of our mineral, we weighed it, we know its mass, and we extracted all the sodium sulfate out, and now that sodium sulfate is floating in our solution. Now we want to know the percent mass of sodium sulfate that was originally in the mineral. So we need to know what mass of sodium sulfate came out of the mineral, what mass is now floating around in our solution. And so what we do next is we add some barium chloride to the solution. The reason for this is that the sodium will bond with the chlorine to make salt, which will stay dissolved in water, leaving the barium and the sulfate to react. We can go back and look at our solubility rules. We know that that is an insoluble compound, and so it will form a precipitate. And so we would then be able to just filter that solution and catch all of our solid. So we added enough barium chloride to react all of the sulfate. We have now captured all of the sulfate in this precipitate, and we filtered it, we've separated it out and let it dry so we don't have any extra mass from moisture or water molecules, and then we weighed it. And now with this mass of our barium sulfate, we can use that as well as the mass percent of sulfate in barium sulfate, which we would calculate using our periodic table. We take the mass of sulfate divided by the mass of barium sulfate. That would tell us what percent of barium sulfate is just the pure sulfate. So we know that percent and we know our mass of barium sulfate that we have created. We could figure out the mass of sulfate in that solid. And then same thing with mass percents, we can figure out how much sodium sulfate must have been present for us to get that much sulfate in our solid. So again, we'd know how much sulfate that we made, and we would know the percent of sulfate in sodium sulfate back here. And then we could back calculate what mass of sodium sulfate we must have started with. Taking that mass of sodium sulfate we started with divided by the mass of our mineral would give us the mass percent of sodium sulfate in that mineral. So that was just one example. I just wanted to talk through a specific example of a process that you could potentially explain or perhaps be given these steps and measurements and have to do those calculations. The other common analysis technique to come up is combustion analysis. And so I would recommend going back to Unit 2, where we've talked about this. There's an example problem in the slides about finding empirical formulas. I would definitely go back and just try that example problem once more, look through it to make sure you're clear on all the steps, because that is a common problem and a really good thinking practice. So the key points on combustion analysis is we've got a hydrocarbon sample. It's definitely got carbon and hydrogen. Sometimes it has oxygen in it. And we combust it completely. So we turn all the carbon into carbon dioxide. We turn all the hydrogen into water. And we capture them. And we know when we measure out the mass of carbon dioxide that we captured, we can know how much carbon we captured. Same with the water. When we measure the mass of water we collected, we know how much hydrogen was in that mass and how much hydrogen must have come from our compound, because there's no other source of either of those two elements. If there was water in our compound as well, we would take the total mass of our compound and subtract out the mass of hydrogen and the mass of carbon that we collected. Whatever mass is remaining must be due to the oxygen. So we know how much of each, what the mass of each of these elements that started in our sample. We convert that to moles, and from there are able to determine the ratio between each of the elements, and that would allow us to determine the subscripts on our elements in our compound. That would give us an empirical formula, the overall ratio between the carbon atoms, the hydrogen, and the oxygen, if applicable. If we also knew the starting mass of our sample, we could go one step further and figure out the molecular formula. So again, I would go back and try at least one of those example problems, because they are a bit long, but they're fairly straightforward if you are familiar with the steps. All right. Another category of chemical reactions that we spent a fair amount of time on are solutions. So remember the terminology here. The solute is the piece of the solution that is dissolved. The solvent is the part of the solution that is doing the dissolving. And when we talk about solutions, one big thing we care about is the solution's concentration. Just because two solutions contain the same compounds doesn't mean they're going to behave the same, because they can have very different proportions, very different concentrations. And the most popular and common way to express concentration is molarity. I know you've heard this several times now, because I think it's been in all of the big idea videos so far. But hey, it's a big idea. So molarity is the moles of solute over the volume of the total solution, the solvent and the solute, the total volume. Now that we have molarity, we have another conversion factor that we can use in calculations. So we had this half of the flowchart before. We know how to get from grams to moles, and we know that we can convert between moles of different substances with the chemical equation. Now we also have this side. Now we can convert between moles and volume with our molarity. Also, when talking about solutions, it's important to remember what is going to dissolve and what's not. So that would be our solubility rules, as well as what's going to dissolve completely and completely ionize and break up, and again, what is not. So things that totally dissolve and totally split apart in water are called the strong electrolytes. And this would include the strong acids, the strong bases, and any soluble ionic compound. And so I've included the solubility rules at the bottom of this slide for your reference. And remember, these are just the general rules of what's going to dissolve in water, or dissolve completely in water. The non-electrolytes tend to be molecular compounds that will not dissolve in water. Acids and bases are some exceptions. These are molecular compounds that do dissolve in water. There are a couple other molecular compounds that dissolve because they are polar and are attracted to the polar water molecules, but many other molecular compounds that are nonpolar won't dissolve in water. They've got nothing attracting them to the water molecules. Let me stay here for one more second. One other thing to keep in mind when talking about solutions was the idea of colligative properties. Remember, this was the idea that in solution, when a solvent has a solute dissolved in it, the particles of that solute interfere with the solvent particles. And so, for example, we know that salt water boils at a higher temperature than pure water. And that's because when salt is dissolved in water, the salt ions, the sodium and the chloride ions, interfere with the water molecules and hold them in the liquid longer. It takes more energy to boil that water, and it takes more energy to get water molecules to escape the liquid and evaporate into the gas, because now they have these obstacles of the other ions. And so that's an important thing to remember. When you have a solution, its properties are going to be affected by the solute. When we've got a solution or a reaction taking place in solution, it's common to write the net ionic equation for it. And the net ionic equation was useful because it allowed us to see exactly what was taking place in our reaction. It ignored any of the ions or any of the pieces that weren't really reacting, that were just sitting by and watching. So we're going to look at a couple of examples. First, a reminder of the key steps. We always start with a balanced molecular equation, so a regular chemical reaction. And then we write a line in which we dissociate or split apart all the strong electrolytes. Once we've done that, we'll just cross out anything that didn't change between the reactant and the product side of the equation. Whatever's left, whatever remains, gets written as part of the net ionic equation. And a reminder, be sure to include charges on ions and include the states of all your substances in these equations, because they're very important. Let's look at a couple of examples. The first one we're going to look at is for a neutralization reaction, so an acid-base reaction. And for any reaction between a strong acid and a strong base, we'll get the same net ionic equation. Let's take a look at this example between hydrochloric acid and sodium hydroxide. So these are both strong electrolytes. This is a strong acid, this is a strong base, and so we know that in solution, in water, this compound is going to completely dissociate into hydrogen ions and chloride ions. We've got the charges on both, as well as their states. They are aqueous because they are dissolved. And same for the sodium hydroxide, it dissociates into sodium ions and hydroxide ions. So these are all the ions on the reactant side of our equation. And then we go to do the same with the products. We've got sodium chloride. We know that that's soluble in water. It's a strong electrolyte. So it dissociates into sodium ions and chloride ions. We've got their charges, we've got their states. And finally we have liquid water. Now this one obviously is not an ionic compound. It's liquid water. It's going to stay written as is. It's not an aqueous phase, it's not dissolved, it's a liquid. And so it just maintains its formula. There's no way to split it up. It's not going to dissociate in itself. Alright, and now once we've got that, we're just going to cross out any ion that appears in both the reactant and the product side unchanged. So anything that didn't really react. So for example, we can see that we've got a chloride ion in our reactant. There's one of them. It's got a -1 charge. It's in the aqueous phase. And we've got the exact same thing on the product side. There's one of them. It's got a negative charge. It's in the aqueous phase. So we can just cross that out. we would call it a spectator ion. It was present in the solution, but it didn't actually change at all. It did not participate in our reaction. Same thing for the sodium ion. We've got one sodium ion, it's got a +1 charge, dissolved, and that's there before and after the reaction. So it really didn't do anything. And so the ions that remain on our reactant side are the hydrogen ion and the hydroxide ion. These are the two reactants in our net ionic equation, and they react to form our only product left over here, liquid water. All right. So the net ionic equation allows us to look past all of the extra ions just present in solution and see exactly which ions are reacting. Now, what if not everything in your equation is a strong electrolyte that's going to dissociate? Well, let's look at this example. If you've got solids or compounds that are not strong electrolytes, you don't need to break them apart into their ions. You just leave them as is. So for example, magnesium hydroxide is a non-soluble or a low solubility compound. So on the reactant side, since it is not a strong electrolyte, we just leave it written as is. Magnesium hydroxide, solid phase. Hydrochloric acid, on the other hand, is in fact a strong electrolyte, and so when we break it apart into its ions, we know that when this dissociates, it will produce 2 hydrogen ions and 2 chloride ions, both in the aqueous phase. Magnesium chloride now is in fact a soluble compound, and it is in the aqueous phase. It is dissolved. So we do break it apart into its compounds, or into its ions. And when this exists as ions, we've got a magnesium ion with a +2 charge, aqueous, and we will have 2 chlorine ions. Remember, we can't have a Cl2 ion because that wouldn't have a charge. We've got 2 chlorines in our solution. We have 2 chlorine ions. When this compound breaks apart, we get 1 magnesium and 2 chloride ions in our solution. Our water, again, just gets brought straight down, unchanged. And so looking at this intermediate step, we can see that the only ion here that would be considered a spectator is the chloride ion. In both the reactants and the products, there's 2 chloride ions that aren't changing. They are just present. They're not doing any part of the reaction. So we will cross those out. They'll cancel each other out. And we'll write down our net ionic equation with everything else. So what's really happening in this equation is that the solid magnesium hydroxide is encountering 2 aqueous hydrogen ions and reacting to make a magnesium ion and 2 water molecules. All right. A couple specific types of reactions with acids and bases are called gas-forming reactions, and we're just going to take a quick look at these. These are reactions that will form the salt and the water, as we expect from acid-base reactions, as well as some other gas that escapes as bubbles in our reaction. So there's 4 cases, 4 types of compounds that will react with an acid or a base to release a gas, and they're listed here. As we can see, we could predict I'll just look at this first one for an example. We could predict the products here because we know we're going to form water. So 2 H's and 1 oxygen are going to be pulled out to form water. And we know we're going to form a salt made out of the cation from one reactant and the anion of another. So that would be the sodium chloride, the cation from our metal carbonate, and the anion from our acid. Alright, but we haven't done anything with the carbon yet. So far we have formed sodium chloride and water. The water required one of these oxygens, and so there will still be leftover atoms to make CO2. That will be our other reactant, or our other product in this example. All right. The other type of reaction that you should be able to recognize are the redox reactions, oxidation reduction reactions. And so there was a brief video on this a couple weeks ago, just to introduce the topic and talk about how to recognize a redox reaction. So if you are one of the 5 people that viewed that, awesome, you can do this. If you're one of the others, you might want to go back and watch that. The main idea is that in order to keep track of oxidation reduction reactions, we assign compounds oxidation numbers. And then of course we've got our memory device. We know that oxidation is loss. So the oxidized agent here is the one that lost, that decreased in oxidation number. So we've got the blue one here. The hydrogen is being oxidized because its oxidation number is decreasing. It is losing electrons. And then we've got reduction is gain. We can see the zinc here is being reduced because its oxidation number is increasing. All right. Here are a couple rules or guidelines for how to assign oxidation numbers. And for the most part, they're pretty straightforward. Elements that are just pure elements in their elemental form will have a number of 0. All right, here we see zinc at a number of 0. There's no charge on zinc, and it's a pure element. The oxidation number of a monatomic ion is the same as its charge. So when it was zinc 2+, it was a monatomic ion. It had a 2+ charge. Its oxidation number was also 2+. Oxygen is typically assigned an oxidation state of -2. You can just use that as a general rule right now. On the redox reaction lesson, we mentioned that there are some exceptions. If the curiosity was just killing you, it's when that oxygen is in a peroxide. Hydrogen is assigned an oxidation number of +1 almost always. You can treat it as always. If the curiosity would have killed you, the exception is that when it forms metal hydrides, like hydrochloric acid. Nope, that one wouldn't count. Like a hydrogen bonded to an iron, or a sodium. Hydrogen bonded to a metal. Then it gets assigned -1. Fluorine is always -1. If we've got a compound, the sum of the oxidation numbers is going to either equal 0 if there is no charge on that compound, or is going to equal the charge on the polyatomic ion if there's a charge on the compound. Alright, we've talked about titration a couple times already as well, but do be familiar with the general steps and the general reasons and concepts behind titration. The idea of titration is to have a way to calculate the concentration of a solution. And so you'll start with one solution of unknown concentration and one solution of known concentration, in which one is an acid and one is a base. You will have some sort of indicator in your unknown solution that will change color when you've reached a certain pH, and then you will begin to titrate it with your known solution. So you will add a certain very well precisely measured amount of your known solution. When you see the color change, you'll know you've reached the equivalence point, and you can perform your calculations based on that. You'll know how many ions you added, because you know the concentration of your known solution, and from there you can calculate how many ions you neutralized. A common standard used is KHP. If you see that one, just remember that this is an acronym for a compound. It is not a chemical formula, and it's used because 1 mole of KHP yields 1 mole of hydrogen ions when it's dissolved, so it makes the math easier. The last analytical technique is spectrophotometry. Again, this came up in a previous big idea slide, but just to mention it one more time, this one uses light to provide information about the concentration of a solution. So here's a diagram of the setup. We've got a light source. We pass it through a prism to split it into its wavelengths, and that passes through a solution to a detector, which knows how much light started from our source and knows how much light it's detected. So what's ever missing must have been absorbed by our sample. And so we get out a result that looks like this, that shows us what wavelengths of light were mostly absorbed by our sample. And this can be useful in calculating the concentration of our sample, because of course things that are more concentrated are going to absorb more light. It's harder to pass light through things of darker, more concentrated color. The Beer-Lambert law expresses this relationship. The absorbance is equal to the path length. A thicker sample is going to absorb more light. The concentration, a more concentrated sample, is going to absorb more light. And the molar absorptivity, the material property that expresses how good that solution is at absorbing light. And once we know all that, we calibrate our equipment so that knowing the path length and knowing the molar absorptivity and measuring the absorbance, we can calculate the concentration. Alright, that's it for this big idea. Go ahead and try some practice problems, or go back and look at other material as necessary, or send your questions if you have them. Thanks.